So far in Chapter 2, we've looked at graphing equations. Today we're going to look at graphing inequalities when you have less than or greater than symbols, and also the same with absolute value. Recall from graphing before with inequalities that when you have a less than or greater than sign, you need to use different types of symbols. So less than or greater than, you want to use a dotted or dashed line. If it's less than or equal to or greater than or equal to, you want to use a solid line when graphing your line out. This equation then serves as your boundary line to the area that is represented in the inequality. So the area that makes all the solutions true needs to get shaded in to show that those are the solutions. Let's try a problem out from your note sheet. So number 1 wants us to graph the inequality 2x plus 3y is greater than 6. In order to do this, we're going to identify the intercepts, the x and y intercepts, and the slope to help us graph this one out. For intercepts, remember you can do that little cover-up method. So if you want to do the cover-up method and cover up the y part to find the x, you got 2x equals 6. So the x-intercept is going to be 3. If you want to find the y-intercept, cover up the x and solve for y, and you get y equals 2. So those are our intercepts. Now we want to find the slope. Now to get the slope of this one, you could, at this point, you could graph out the intercepts and graph the line. Sometimes finding slope helps too. Now if we're going to find slope here, we would want to solve this equation for y. So we got 2x plus 3y is greater than 6. Let's solve that for y. So first we'd start out by subtracting 2x from both sides. We don't need to do anything with the sign because we haven't multiplied or divided by a negative. Now we got to get rid of this 3. So now we're dividing by 3, and we divide everything by 3. Since 3 is a positive number, we don't need to change the direction of the sign. So it'd be y is greater than or equal to negative 2/3 x plus 2. So our slope in this one is negative 2/3. It's the number in front of x. All right, let's graph this one out. So over on our graph, we now have enough information to graph this problem. So our y-intercept we said is 2. Our slope is negative 2/3. That means we're going down 2, right 3. So if we go down 2, right 3, we got a point there, down 2, right 3. Or we could go the opposite way, up 2, left 3. And there's our points. Notice it does have an x-intercept of 3, just like we said it should. Now we want to graph that out. Now we got to look at the symbol over here. The symbol is greater than. That means if it doesn't have the or equals to, we want to use a dotted line. So this one, instead of a solid line, we're using a dash or dotted line here to represent our boundary line. That means the points on our line itself are not solutions. All right, there's one last thing now we need to do on these inequality ones, and that is decide which side should we shade on. And to decide that, we're going to test a point. And the test point is going to tell us if it comes out true or false, which side our solutions are on. The easiest test point to use is the point 0, 0, the origin. If we check the origin, that'll tell us whether or not the origin is a solution or not a solution. The only time you can't use the origin is if the line itself happens to go through the origin. This one does not go through the origin right in the middle there, so we should be all right. So now we're going to test out 0, 0. So to test 0, 0, we're going to plug the point 0, 0 in and see what do we get when we test that out. So the point 0, 0 is going to get tested. So we're going to plug 0 in for x, 0 in for y, and see what happens in our problem here. So 2 times 0 plus 3 times 0. The reason 0 and 0 is nice is anything times 0 is 0. So we got 0 plus 0, which is 0, greater than 6. Is that true or false? Is 0 greater than 6? That is false. So this point, 0, 0, came out to be a false point, which means it's not a solution, which means all our solutions are not on the bottom left side of our graph, they're on the top right side of our graph. So that would be the side of the graph we're going to then shade in. So all our solutions are in this upper part of the graph. So that's the side of the graph we shade in. All right, for tomorrow, why don't you guys try number 2 out? See if you can graph that one out. Find the intercepts, find the slope, graph it out. Remember what type of line you want to use, and make sure you test the point and shade in at the end. All right, number 3. This is a little bit of a word problem now. They want us to find an inequality to represent the situation, then answer some questions. All right, first one says, Manny has $15 to spend at the fair. It costs $5 for admission, 75 cents for each ride ticket, and 25 cents for each game ticket. Write an inequality for the number of ride and game tickets he can buy. Well, if Manny has $15, he can't spend more than that. So we got to make sure whatever it is less than or equal to 15. So what does Manny spend his money on? $5 for admission. He's not going to have to repeatedly pay for his admission. That's a one-time cost of $5. Plus 75 cents for each ride ticket. This word each indicates it's going to be more than once, and 25 cents for each game ticket. That again tells you he's going to be doing it more than once. So we have two different variables here. 75 cents for each ride ticket. Let's use R for ride. And 25 cents for each game ticket. Let's use G for game. So that inequality represents the number of ride and game tickets. So we could do probably one thing to simplify this a little bit as we go here. Let's subtract admission right away because we know he's going to have to pay for that admission to get in. So really, he can spend some combination of 75 cents on ride tickets, 25 cents on game tickets. That has to be less than or equal to the $10 he has remaining after admission. All right, let's answer some questions then. For number 3, if he buys 10 game tickets, how many ride tickets will he be able to buy? Well, 10 game tickets, we got to figure out where should we substitute that into our equation. That's game tickets, so we should plug 10 in for G and see what we get. So let's see, we got 0.75R plus 0.25. We're buying 10 of those. Has to be less than or equal to $10 he has left. Do a little multiplication. And he's spending $2.50 on the games. Subtract that from his $10 he has. And he now has $7.50 remaining. Divide by 75 cents. And it looks like he can do 10 rides or less. So that's the answer there. All right. Next one, it says, what is the maximum number of ride tickets he can buy? Well, if he wants the maximum number of ride tickets, we want to try to keep all the money he has for rides. How many game tickets should he buy if he wants the maximum number of rides? You don't want to buy any game tickets if you want to see the total number of rides. So on this one, we would plug in 0 in for the game ticket. So 75 cents times the number of rides plus 25 cents times 0 game tickets. 0 times anything means he's not going to be spending anything on game tickets. We just want to do it all on rides. So divide by 75 cents and we get that R has to be less than or equal to 13.3 rides. We can't go on a third of a ride, so it looks like he can afford to get 13 ride tickets. That would be the maximum number he could get. For tomorrow, see if you can answer the last one there. What's the maximum number of game tickets he could buy? So try that one out for tomorrow. All right, let's go to the back of your sheet. Yesterday we looked at this absolute value function and some things about it. Remember, absolute value always, when you plug a number in, makes the number positive. So if we plug in negative 3 into the absolute value of negative 3 is positive 3. Absolute value of negative 2, positive 2, and so on. Absolute value of 0 is 0 since it's distance away from 0. That's not any distance away. Distance away from 0 for 1 is 1, 2, and 3. Everything should be positive. And we graphed this one out and looked at what the graph looks like. We have the points 0, 0, 1, 1, 2, 2, 3, 3. We also had the point negative 1, 1, negative 2, 2, negative 3, 3. Connecting those, you get this absolute value graph. Notice the slope on each side. The slope on this side is up 1 over 1, so it's a slope of positive 1 over 1. On the left side, it's down 1, right 1. So the slope on that side is negative 1 over 1. All right, now a couple things to remember when you're graphing absolute value that we also talked about. If they start throwing other numbers around with the absolute value problem, whatever's inside the absolute value of x shifts the vertex to the left or right, and it's always the opposite. Vertex being this point right here, that's the vertex. So any number inside, you do the opposite, left or right. If there's numbers outside the absolute value that's added or subtracted, that moves the vertex up or down. If it's positive, it's up. If it's negative, it's down. So as an example, let's say we have the absolute value function, f of x equals absolute value of x minus 5 minus 2. What is that graph going to look like? Well, it should be the same shape as this one. We should have the same V shape. The vertex is going to be moved though. What are these doing? This would shift it left or right. And we said if it's inside, it's opposite. So if it's negative, it's actually going to shift 5 to the right. Outside, up is positive, down is negative. So this would shift it 2 down. So if we graph that one, the vertex would be 1, 2, 3, 4, 5, down 2. The vertex would be right here. And we'd have that same absolute value shape. So the slope on the right side is up 1 over 1, up 1 over 1, and so on. The slope on the other side is negative 1, so you go up 1, left 1, up 1, left 1, and so on. The slope on that side would be negative 1. So it'll always have that V shape. Okay. So for tomorrow, I want you to try graphing number 4 and number 5 out. See if you can graph both the graph on number 4 and number 5, either making an in-out table to do it if you're really not sure, or if you remember some of the stuff we talked about shifting, you could also use that. And we'll check those tomorrow.